So good morning, everyone. Welcome also at the first Enerstock online conference. My name is Bert Gysen, and since the beginning of January, I'm the chair of the Energy Storage Technology Collaboration Program. Now, before we start this conference, I would express my sincere condolence with all the victims in Turkey and Syria. We all see the damage and the suffering here on television, but unfortunately for some of our colleagues, it is reality. So, my dear colleagues there in Turkey, take care under these terrible circumstances. So, why this online Enerstock conference, while we already have our Enerstock conferences every 3 years? Well, for the simple reason that the whole energy system is changing at an incredible pace, and we see that there is a constant need for more, but also more accurate information. So we thought that it would be good to have some kind of a midterm smaller conference, and the Enerstock online conference was born. So it's a conference where we also want to focus, of course, on storage, but also on storage in all its aspects. So not only about technology itself, but also on economics, education, social aspects, and so on. I would also like to take this opportunity to invite you already to our next Enerstock conference, which will take place in Lyon, the 2 to 6th of June, 2024. So please mark it already in your agenda. Going back to the program of the day, as Stephanie already said, there are 4 speakers. We have a total of 8 speakers today, 4 before noon and 4 in the afternoon. Also, again, I want to repeat, if you have questions, please put it in the question and answer box, and then we can talk about it later, discuss it later on. So, but why do we need energy storage? Most of you know, of course, that if we want to achieve a net zero CO2 emission in 2050, that we need to evolve to a renewable-based energy system. An energy system where electricity will move into the heart of this system. And as a consequence of this intermittence, energy storage becomes crucial for providing the necessary flexibility and also for sector integration, so that we can provide the right form of energy at the right time, at the right place. The result is that today energy storage gains in value, and as we all know, as something gains in value, it also attracts more scientific, public, and luckily also political interest. So we will evolve to a more complex energy system. A system coming from production follows demand to a system where flexibility is key, and where storage is at the core of this new energy system. We have batteries, we have water boilers, so most of the people say, what's the problem? Aren't we then ready for this new, more complex energy system? Or do we still facing some challenges? And indeed, there are still a lot of challenges. Here, I will mention some technical challenges. I'm just mentioning a couple of them. If you look to the more technology-specific challenges, and that's independently of which type of storage we are using, we have a lot of challenges related to the compactness of storage. We have challenges related to charging, discharging capacity, to safety aspects. And we see all, even this week, I saw some pictures of burning cars, the problem of the lithium battery. We are talking about sustainability and the discussion on the rare materials, the mining of the materials. We are talking about circularity, so a lot of challenges ahead of. There are also challenges related to the optimization of the grid infrastructure, where storage can play a major role. If you look to demand response and if you look to the bidirectional communication which is needed, as storage is part of the energy system. And of course, we all know Internet of Things is growing, artificial intelligence becomes part of our daily life. So also here, we have to see it gives us extra possibilities to the integration of storage into the energy system. And last but not least, the whole flexible sector coupling, and where electricity meets heat, where electricity meets transport, where heat meets transport, and vice versa. So a lot of challenges ahead of us. But it's not only from a technological point of view, there are also still a lot of economical challenges. On a system level, we can have certain benefits by using storage, but how can this be translated into monetary value? And how can this be translated into business cases, thereby improving our asset value and contributing to the security of supply? Changing to a more decentralized energy system will also bring new value chains. But often the regulatory framework is not following and is more a barrier toward further technological developments. So also here we have to work on. Also, we have to take into account the whole sustainability aspects, the end of life, recyclability, circular economy, and so on. And that gives us, again, opportunities, challenges, if you want, related to new value chains. Now, before I show you how our TCP contributes to the further development of the energy system and the challenges, I think it's good to know that we operate under the umbrella of the IEA, the International Energy Agency. Within this technology network, more than 6,000 experts are active and working together. So it forms a unique technology network of 40 collaboration programs called the TCPs, where the energy storage is one of them. So it's a real global collaboration and represent an essential forum for governments and industry, which is quite important because we still have to convince the governments of the knowledge of the necessity of storage. It's open, and that's good to know. It's open to IEA members, but also to non-member countries. So there are different ways to join the TCPs, the technology collaboration programs, even if your country is not a member of the IEA. It deals with a lot of things as energy efficiency, renewables, fusion, hydrogen, even fossil fuels still. And we are looking for cutting-edge technologies, research, development, innovation of energy technology, and all the outcomes of the different programs. They provide the basis for the IEA analysis, and you can see their annual reports on the websites. And it's also the basis for international public and private research partnerships. But let's focus on our technology, the collaboration program of energy storage itself. So it's an international R&D collaboration, which already goes back to 1978. So it was one of the first TCPs within the IEA. And today, 21 countries with even more than 100 experts are participating in this TCP. If you can, you can see it on the slide. It are countries from Europe, America, and also from the East. So it's, I think, the world's largest energy storage networks. We anticipate on the energy system transformation. We're looking for all kinds of solutions to battle climate change. And of course, we cooperate with other organizations and TCPs. Why? Because storage on its own, of course, has no value. It's always part of the system. So it means we cooperate with other TCPs related on heat pump, related on district heating and cooling, with solar, and so on. We promote the increased deployment of energy storage, and quite important, we also develop key messages for policymakers and also for the IEA analysis. So our mission is to contribute to the transition towards a renewable energy system by the use of energy storage through joint research, design and development, and pre-standardization work. We actively disseminate our results, and we include the industry as much as possible. We promote a more holistic approach to the energy system because, as I said, storage cannot stand on its own. We have some research priorities. It's about thermal storage, electrical storage, hybrid options, and modeling. So within our TCP, R&D is done within so-called tasks. It's not only within our TCP, it's in all the TCPs. It's task driven. So all the work is done within different tasks. More information on the task you can find on our website, and I will show the link later on. But if you look to the tasks, there are quite a lot of tasks running at the moment. And 5 of these tasks are related to energy storage in energy systems. So all the tasks are numbered, and we see that task 32, it's about modeling of energy storage for simulation optimization of energy systems. And the outcome will be open source energy storage models. In task 35, we look into flexible sector coupling and the distribution of renewable electricity to other sectors by energy storage. Then we have another task, task 37, on smart design and control of energy storage systems, where we look to the artificial intelligence for net zero energy buildings. Task 39 goes on large thermal energy storages for district heating, and it's about the decarbonization of district heating system and the enabling of a more flexible operation. And last but not least, task 41, it's about the economic assessment of thermal energy storage. ECO in Nesto is the title, so it's about economic analysis for supporting the deployment of energy storage. We also have 4 tasks related to technology improvements. One of them is the comfort and climate box, where we bring together heat pump and storage. It's task 35, and it's also task 55 of the heat pump technology TCP. Another one is task 36, where we look to Carnot batteries, and we go for looking for an inexpensive site-independent storage of electric energy by use of the Carnot batteries. Task 38 is on ground source de-icing and snow melting systems for infrastructure, where we try to use geothermal heat in an environmentally friendly and energy efficient way. And task 42, it's about large-scale, medium duration energy storage, where we try to solve the intermediate time gap in balancing demand and supply. And our last current task is task 40. It's related to materials and components, and we look there for compact thermal energy storage materials within components, within systems. It's about PCM and TCM development and standardization. And here it's also cooperation with the solar heating and cooling TCP. As mentioned in our mission, we want also to disseminate our results, all the results from those tasks, as much as possible. And one of the means is the Enerstock conference, as already explained at the beginning of this presentation. It's a 3-annual Enerstock conference, and this one and the online conference for the first time is also one of the means to disseminate our results. And we also promote the active participation of all of experts in symposia, workshop, webinars, and we have our own on-seminar series. So every month we try to have an online seminar. We also record them, and you can find them via the YouTube channels. So if you want to look at it, go to this link. So if you want more information, I would say please take a look to our website. You can always contact us if you want to participate in one of the tasks, or if your company wants to become a member of our TCP. And of course, you can also sign up for our newsletter. So thank you for listening. I wish you all a very fruitful conference. And now I would like to give the floor, or should I say the screen, to our next speakers. Thank you.
So yeah, thank you very much. So being here the follower speaker of Bert, and thank you for bringing up all the economical challenges, because that's the key of my presentation within the next 15 minutes. So my target group are basically investors, and as we've learned, energy storage systems are quite complex. So it's really important to set up an ecosystem so that investors game or getting access to the market intelligence to make proper and good investments. So just a quick overview what's going on the next 15 minutes. So I'm just giving some basic questions. What's the thing about making money with energy storage systems, and then the next and the third chapter is basically from benefit to business case. So it's quite important always thinking an application, because the application is relevant then to qualify or quantify the value of the energy storage. Exactly, and then the fourth chapter is basically what's going on in the market. So I mean, there are plenty investment opportunities. But maybe just 3 sentences. So what is here Decarbonization Investment Advisory Services? So I'm quite closely with the Energy Storage Systems Association. And so one fact we find, it's very important to bring investor and potential targets together and set up the market intelligence to bring a good opportunity sourcing, so to find good targets and to get the experts together to have a due diligence excellence. And then in the third part, and I think that's really the important one, to get also a value creation process ongoing. So that's why I'm really happy also to talk here in this expert audience. And so then just let's go on with what are the levers of making money. I think we just heard it. So why do we need energy storage in decarbonized energy world? Yeah, it's about flattening the curve. I mean, here you see the 3 major markets of the energy system. It's about the energy generation, it's about the distribution, and about managing the grid. And then finally, it's about how to bring the energy to the end consumer. And I think, as we all know, okay, the distribution is quite a thing with renewables, as they're quite volatile. It's having the energy at the right place and at the right time. And so, which is also an important point here, which is stressed, so that energy is not basically electricity, as we all know. It's and the majority is just thermal energy, and which is about 50%. And so this is a very important point. I'm telling to investors that the solution to green energy availability are energy storage systems, because they are key in matching supply and demand so that you have the energy available when needed. So what is the second important point? What do we expect from energy storage systems? There are 2 things. The one is energy. Of course, we want to have it constantly at peak times. And the other thing is we need the power. We want to charge our cars fast. So we need some kind of buffer batteries. And so here are the examples that you have, a bathtub, etc. So this is, I think, just important to mention that it's not easy to just make money with energy. So power is the new currency. I want to have the electricity, I want to have the heat, the cold, just in a very quick time, just when I need it. And so here, this is also just a good comparison that you see here. I mean, you have here EV charging station where okay, I want to charge my car within 15 minutes. And here you have a seasonal thermal storage, just the water storage. And I come to that example also maybe when we talk about long-term duration energy storage systems. So which actual service and benefits can be identified? I think you might know Swiss pocket knife. And so this is the great things about energy storage systems, because they are multi-tools. And so this is also the good thing then coming back to business cases. It's just about that you have potential of multiple benefits and revenue streams. So just having it at one glance, so there are lots of benefits delivered by energy systems, by energy storage systems. You have the flexibility, you have the reliability, you get also autarky, and of course mobility is we couldn't use electric vehicles or mobile phones without batteries. So when do we make money from energy storage? It's it's basically the 3 things. You make money by charging, and you make money by discharging, and the optimal case it's that it's a circle. So when you have discharge, you're charging again. And at the moment, we do not have a business case for just storage or energy being stored. You get money either when it's charged, maybe for ancillary services like stabilizing the net, or for, of course, discharging the energy. So, but maybe this is just a very simple overview, but I think it gives a good, it explains pretty well what long duration means. So if you have a low frequency in your charging process and in your discharging process, you need to have a really very or value for money or inexpensive storage that you have a really proper return on invest. So so then we come to crucial questions. What is relevant from benefit to business case? So the benefit here, those are 4 questions. I give examples here. For example, you see here a really deep tech, great vision, the vision of smart homes connected to utilities. So we have something about 40 million fridges in Germany. And if you would connect them with really just a very or quite inexpensive storage or cold storage, you could provide a lot of electric power capacity of over 1 gigawatt. The thing is, okay, you have to ask a question, who will pay for it? And at the moment, it's quite difficult that you really say, okay, the grid operator doesn't pay, or nor the producer of the fridge. So I've brought a second example. So, and Bert also has shown this as one of the working groups. It's a seasonal heat storage, space heating in Munich, in the north of Munich. And so this gives a really good example. This is not really deep tech, but it's actually working. So you have a heat and domestic hot water supply of 320 apartments. And get at least partly autarky by having this heat storage. All right, and so here, this is just from benefit to business case. Again, quite important slide, because the application and its usefulness is key from a customer perspective, because ultimately the technology needs to match the application. So this is really always the thing having in mind. It's the triad. Okay, what's the application? What technology is matching to the application needed? And so that you can just quantify and qualify the concrete benefits. Yeah, having it at one glance, the return on invest, of course, depends on the number of charging, discharging cycles per time. And then always think energy storage within applications. Only then we can quantify the value of energy storage. So now I just give a very quick overview. So how do we approach the asset class of energy storage systems? So this is an important slide for investors, because most investors, or especially the institutional investors, they look for maybe a big PV power plants or offshore wind parks and want to invest into the grid, which are important investments. But the key for a decarbonized energy system will be a decentral prosumer world. So that exactly brings that what I've told before. How will the technology match the application to bring the value to the prosumer's need? So, and here, this is maybe we also heard it in the keynote from Bert. It's really the ultimate goal is just to get a decarbonization in combination with security of supply and thus energy autarky at stable cost. So, and there is a multitude of energy storage opportunities with high investing potential in tomorrow's energy system. So there is a huge market in the industry and in the commercial area. So we've heard a lot about electricity, but now the thing is how to get the power you need and the process heat, etc., the heat, the cold, the mobility concepts. And so this is with the strongly rising e-mobility infrastructure. So there are a lot of startups, joint ventures like Numbot, Yolt, where they make deals with etc. with retailers, how you charge your cars A, fast, and B, how you get the possibility to charge your electronic vehicles with green electricity. So another example of the application grid stability for utility services is, of course, you have big pumped hydro storage and you have battery storages. We will hear a keynote from Fluence later on, and of course you have power to X and hydrogen as a good energy storage system as well. So here, this is one example for a grid booster concept in Germany. And so there are many more investments to come like those stabilizing the grid. And yeah, so I come to my final slide. It's just that rethinking alternative asset investments. So because institutional investors think in infrastructure and they think in renewables, but it's all about decentral renewable infrastructure enabled by energy storage, which is the crucial tool to get a decarbonized energy world. So thank you very much.
So I'll say something on thermal energy storage for industrial processes. To address this topic, I would like to start with targets for industry as specified in the Dutch climate agreement. So targets for the Dutch industry. So this is a quote. In 2050, the industry is circular and emits virtually no greenhouse gas anymore. Factories are running on renewable electricity from solar and wind, or energy from geothermal sources, renewable hydrogen and biogas. Waste heat is used in the industry itself or exports to greenhouse or the built environment. So what we see over here is indeed in 2050, we have, well, there is a huge challenge in reduction of CO2. And well, if we look at these proposed solutions, what we see is geothermal sources is definitely interesting, but potential for the Netherlands is somewhat limited also to, say, about 150 degrees. So for industrial heat demand, that is relatively low. Biogas, we expect we need most of our available biomass more as feedstock than as fuel. Renewable hydrogen will in the end have to come from renewable electricity by solar and wind. So in the end, what we heavily are relying on is renewable electricity from solar and wind. If we look at the present energy demands in industry, in Dutch industry, you can see that, say, about a quarter is electric demand, 3/4 is thermal demands, heat. So if we have to provide all this heat by conversion of power to heat, we need huge upscaling both of renewable generation and of grid capacity. Now let's have a look at what at the industrial heating demand. So over here you see the final energy demands in the European industry, and we can see that most of this energy demand, as expected, is related to process heating. And typically, say, in the order of 1/3 is below 200 degrees, mainly provided by steam boilers, industrial steam, and 2/3 is above 200 degrees, related mainly provided by furnaces. So all this heat would then have to be electrified, and for low temperatures we would focus mainly on well, one of the interesting options is industrial heat pumps. For high temperatures it would be more direct electric heating. So what does that mean for heat storage? Well, energy efficiency is a requirement for electrification of industrial processes. As we have just seen, we need huge upscaling, also in renewable capacity availability. Since renewable availability will be a limiting factor in the end, we need to be efficient using this energy. We will have grid capacity constraints, and also there's the issue of competitiveness with countries having cheaper solar and wind. So also a good reason to be energy efficient. So at one hand, we need energy efficiency to reduce energy use. And important topics there are, for instance, waste heat recovery and reuse. So to minimize the amount of waste heat. And we can do that by, for instance, short-term heat storage applied to batch processes, so we can store the heat of one batch, upgrade it with a heat pump, and use it in another batch. Or preheating of batches, also requiring heat storage. Also, if we want to use waste heat to be provided to district heating, we would have long-term storage connected to this district heating system to do this in an optimal way. Furthermore, we have heat storage related to emergency backup, say an interruptible thermal power system supply, replacing, for instance, standby steam boilers, and thereby foregoing emissions of these boilers. So that at one hand, we have the energy efficiency issue. On the other hand, we have the integration of renewables. And if we look at renewables, that will be first and foremost power to heat, converting fluctuating electric supply from solar PV and wind. In addition, we will have in Europe some solar thermal supply, but probably not much in the Netherlands or in the north. And we will have constant thermal supply from geothermal. That also requires storage if you want to match it to fluctuating thermal demand in processes. So we see a lot of roles here for heat storage. Now, what options do we have for heat storage? Well, this is just a very basic slide. So over here we have temperature range, different types of heat storage, sensible, phase change, so storing in a melt solidification, sorption heat storage, thermochemical, and chemical heat storage. If we look, in terms of TRL, we can see that sensible heat storage is quite well developed and is applied on a significant scale in the market already. That can relate to liquids, so heat storage in water, thermal oil, molten salts, but also solids going to much higher temperature, to 800 degrees. The other types of heat storage are still at lower TRL. We are doing work, among others, on PCM heat storage. Sorption heat storage, hydroxides can provide high temperature heat, and chemical heat storage. And chemical heat storage is, among others, related to renewable hydrogen and fuels derived from renewable hydrogen, such as ammonia or redox heat storage. This redox heat storage, I'd like to say a few words on, because I think it's an interesting technology. So basically, what we have is iron oxide powder, metal oxide, for instance, iron oxide. We can reduce that to pure iron by renewable hydrogen and renewable heat provided from power to heat. And this iron powder we can store for whatever time we want. And if we need the heat, we can combust the iron powder, providing heat to our required applications. And as you can see over here, in terms of energy density, from sensible to chemical heat storage, we see a significant increase in energy density. So it is interesting to also look at these lower TRL options. One of the topics we are working on at TNO related to energy efficiency is this example of industrial steam storage. So over here, it's a PCM heat storage. Related to the purpose of this PCM heat storage is heat recovery from exothermal batch processes. So we recover this heat, store it in the PCM. When needed, we use this charged PCM to be discharged producing steam, low pressure steam that can be upgraded with steam compression. Over here you see the storage. Within the storage we have a large number of tubes, as also shown over here. And these tubes are filled with phase change material. The phase change material used as storage material gives a good match with the generation of steam at a constant pressure and temperature. So PCM and steam are an interesting match. We use adipic acid in this material, melting at 150 degrees. We can charge this by low pressure steam coming from the external batch process. And if we discharge it, we flow a water film around the surface of the tubes. The water evaporates, producing low pressure steam that we can upgrade with this steam compressor. And in order to get sufficient power, we need thin and long tubes filled with high conductivity phase change material. We increase the conductivity by adding graphite, resulting in conductivities in the order of 5 watt per meter Kelvin. Another type of project is related to this integration of renewable electricity. And that is something we looked at in the SPOT project, trying to answer the question how much generation, conversion, and storage is needed to cover industrial heat demand fully with renewable electricity, just as a kind of limiting case to get some feeling for order of magnitude. So what we made some assumptions regarding the industrial heat demands. So it has to be met fully by renewable electricity from solar and wind. And the demand itself is constant over the year. So we have a fluctuating supply and a constant demand. So how much storage capacity do we then need? For the scenarios, we use scenarios that are supported by the Dutch Ministry of Economic Affairs related to the industrial energy demands and the solar over wind ratio. And then if we look at the amount of storage needed in the graph, we can see that it for these different scenarios, we can see that it strongly is influenced by the ratio of wind over solar, as one might expect. So on top, we see 70% wind, 30% PV. And at bottom, we see 60% wind, 40% PV. I'm not sure if everybody can see my pointer. So over here, we see 60% wind, 40% PV. Over here, 70% wind, 30% PV. And the optimum is, well, somewhere in the middle. But in all cases, we will need a significant amount of heat storage to meet this, in the order of at least 2.5% of the annual demands or more if we have lower conversion efficiency in the system. So if we, from this information, we try to calculate the costs of such an energy system. So what we did is we compared different conversion and storage routes. So to explain, suppose if you want to go from electricity to heat, you can store the electricity and then discharge the storage to provide electricity to a heat pump that we can use to provide the heat. Or we can have the electricity converted to hydrogen, store the hydrogen, combust the hydrogen, and thereby provide the heat. So we have different conversion and storage routes. There are a lot more, but these two are just two examples. And over here you see the different conversion and storage routes that were investigated. What we saw is that depending on the scenario, so we have two cases below 200 degrees, because there we can use heat pumps, and above 200 degrees where we cannot. What we saw is that the total costs to provide the Dutch industry with this electricity for heating strongly varied, depending, first of all, on the selected conversion and storage technology. Secondly, on required infrastructure, whether it's a hydrogen network or an electricity grid. The electricity grids being a lot more expensive for a given power than the hydrogen network. And also the conversion efficiencies, because if we have a lower conversion efficiency, it means we need more renewable generation, which comes at a cost. So comparing all these options, what we saw is that the cheapest options were below 200 degrees to provide this heat by means of a heat pump and heat storage. And above 200 degrees, use hydrogen and cavern storage. However, these are two generalized solutions. What is the best solution in individual case will depend on local conditions. And how important these local conditions are is also illustrated a bit by the next slide. This is current developments in the Netherlands. What we see is that start of electrification in the Netherlands is presently hampered by grid capacity constraints. If you look at this map of the Netherlands, we see the yellow parts have a risk of transport constraints. Orange is structural congestion announced, and red is structural congestion is already there and no new transport requests are possible. So we see that there is a lot of pressure on the electricity grid at the moment, and that we still have to expand towards the power to heat. However, what we also see is that this already triggers questions on heat storage. For instance, we see sometimes small companies having large PV installations who cannot feed back their electricity to the grid. And we get questions on, is it possible to use this electricity from the PV, for instance, in weekends when the production is not running, and store that, for instance, in heat storage that we can supply it again during the week. So already here, these grid constraints trigger questions on storage. So conclusions. Large increase in industrial electricity use is expected because of the industrial electrification that is coming. That will be by different forms, by industrial heat pumps, direct electric heating. So industrial heat pumps, I mean heat pumps going up to 150, 200 degrees, upgrading waste heat to process heat. Direct electric heating for higher temperature processes, and also mechanical drive. Well, for heat pumps and direct electric heating, we will need storage to integrate it properly. Then industrial heat storage will become much more important because of efficiency increase and integration of renewables. Grid constraints will be an important concern, but also gives opportunities for local storage, including thermal. And policymakers, industries, technology providers, and R&D need to cooperate to bring these technologies to the markets. And therefore, we, in the era, white paper was written by, among others, TNO, but also several other institutes. And just to give you a flavor of this white paper, over here you see some of the recommended actions for policymakers. Among others, electrification of industrial processes will strongly enhance the need for heat storage, which needs to be recognized. It's important that there is support for the demonstration scale-up of energy storage, provide support for dissemination of best practices for integration, just to make the technology more widely accepted, more easy to implement, and provide support for targeted R&D programs to bring the low material technologies to the market. Well, I will not go in all of them. Also, we have recommendations for technical and business recommended actions, and those can be found in the white paper. And over here, you see the link to the white paper for whomever is interested. And that's what I wanted to say. So,
sorry. Now I should be unmuted. I had to find where the unmuting button was after sharing the screen. Thanks, Stephanie, and thanks for the invitation to speak at today's Enerstock conference about the value of storage. And over the next 50 minutes, I want to talk about the economics behind large-scale battery storage. This is, in principle, like globally applicable, but I will do it based on a very specific German market to highlight developments that we're seeing in markets around the world. Regarding myself, I'm responsible at Fluence as part of our growth team for the German, Belgian, and Dutch market, and also for battery storage for transmission system operators in the EMEA region. And this is where I want to talk to you today about. So very quickly about Fluence, our mission is to transform the way we power our world, and we want to do that by integrating storage into electricity grids. What you need to know about us, we're a global market leader for energy storage products based on battery technology. We have about 5.5 gigawatt of battery projects deployed globally, deployed or in deployment globally, and more than 1 gigawatt of those are in Germany. Are in Europe, not in Germany. In Germany, we have about 350 deployed or under deployment. So quickly, why do I talk, or why do we look at the battery energy storage only? Because it's a huge growth sector. So this is a graph from Bloomberg. You see we're down here at the moment from the scale of the battery storage market, and we really see it go up tremendously over the next decades. And I think one thing to always remember is the scale that the global battery storage market will have in 2050 compared to today. We are only like, I think, 6% of where we will be in 2050. So, I mean, we have a great journey ahead of us. But the question is, of course, what will battery storage do in electricity grids? And how is this changing from what we all know about battery storage today? So let's maybe take first a step back. What are actually the drivers? And this is just a very general overview. We do, of course, have a lot of policy drivers from renewable targets, renewable integration targets, specifically in Germany, but in other countries as well. We're facing the phase out of, or we're looking at the phase out of nuclear and generation of coal generation. So we are generally on a move away from away from thermal power generators to renewables. And this comes with a challenge that Vanessa had mentioned before already as well, that we need to move energy around from time of generation to time of consumption. On a policy landscape, we do, of course, also see a lot of movement in enabling this, this transformational change that we're seeing in our electricity system, with market reform being debated on European level, on German level. Specifically in Germany, we're looking at price zone split, so basically providing more locational signals to energy prices in the market. If we take a look at like what was the past, I want to say the past of energy storage in Germany, there was a lot of very small projects spread all over Germany. I think we see here we have more than 75 megawatt scale battery projects in Germany, but only 4 of them are larger than 25 megawatts. So a lot of small projects, and we're currently in a transformation to see what we call mega projects, or what we call in different countries. Mega projects differs. So in the UK, I think we see 400 megawatt projects being built. So in Germany, we're getting to a place where we see 100 megawatt blocks batteries being built into wholesale markets. And this is really a bit of a transformational change from where we have been in the past. This trend is also, by the way, underlined, which is quite interesting, in the scenario planning of the German grid operators, which was approved by the German regulator, where 2 years ago they had expected only about 3 gigawatt of battery storage to be part of the German electricity grid by 2035. And they went from forecasting 3 gigawatt of battery storage to around 24 gigawatt of battery storage to be integrated in electricity grids in Germany in 2035 or 2037. And the key driver behind this is the integration of storage into wholesale markets. So when we look at battery projects in Germany, traditionally, they have been mainly active in what we call FCR and FRR, which are frequency regulation products. So these are batteries which will have to react within seconds to keep power grid stable, to keep the demand and load and balance and the frequency of 50 hertz stable. And these ancillary service markets, frequency regulation products, are typically, we have seen that in many markets around the world, the first kind of wave of battery storage projects coming into a market, because these kind of very fast response requirements are a perfect fit for batteries. However, this is a kind of, I almost want to say, a niche market. It has a limited cap. It can saturate very quickly, and that's what we've seen in Germany as well, this market segment saturating. So we're also in Germany now seeing like a move into wholesale market products. So just here to compare, the balancing markets is a service that is provided by system operators. And we're now moving into the wholesale market which has much larger volumes, where we go into spot market trading and day ahead and intraday auctions. And I'll talk a bit more about those in a moment. Why is this relevant? So first of all, it's relevant. We saw before this pocket knife energy storage being the Swiss Army knife of the energy transition. I think a graph created by the German Storage Association, BVS, and I think Vanessa used it before as well. The key for storage to be deployed in different market segments is their capability to stack different revenues on top of each other. So energy storage being able to provide frequency regulation when prices are good there, but also to move into other applications when prices are good there as well. And there we've actually seen key changes in the market for frequency regulation in Germany and across Europe, where previously you would provide frequency regulation for 1 week at a time. Now you can provide frequency regulation for 4-hour blocks, which provides much more flexibility for storage to enter other markets. Again, why is this relevant? Because now we actually have a number of different market products that energy storage can bid into. You see they have different market volumes. So the frequency regulation products have about 600 megawatt. And if we go into secondary frequency regulation, the AFFR, we talk about 2 gigawatt of volume. But then if we look into wholesale market trading, we're getting into gigawatt hours of volume traded every hour. And this is like the scale and the size of markets in which energy storage can make a real impact and a real potential. So what does this mean, energy wholesale trading? Energy wholesale trading, and I mean, we have touched on it before, is trading energy on the spot market, where you get a price signal for what electricity is worth. You can check like your hourly prices on, for example, Apex Spot. Down here is just one of those graphs. It's from sometime last week. Last year, I probably should have taken a graph from this week, where I think the spreads are a bit lower. But what we typically see that electricity is cheaper at night because there's very little demand. A lot of conventional power plants are generating. In the morning, when people start to wake up, switch on their light, industry process ramp up, electricity gets more expensive. During the day, when solar is generated, prices go down again because we have a lot of volumes of cheap renewables in the grid. And towards the evening, when the sun goes down, people come home, we see peak electricity demand, prices go up again. So this is how typically wholesale prices behave. And here we see these kind of spreads. So the difference between low prices and high prices, this is exactly what storage does. It buys electricity at 250 euros per megawatt hour at night, and then it sells it, in this case, at 370 in the morning. And then it can buy electricity again when it's cheap again and sell it again in the morning. And this is basically the arbitrage model, which is enabled by buying and selling electricity in the day-ahead markets, where every day, like day before delivery, this market takes place, where we're matching suppliers and the demand for the next day. But the day-ahead market, it doesn't stop there when we think about electricity trading. Because, okay, here's just another graph from the Netherlands. I think that was I had a little competition last year. Of course, last year we had really high volatility in the markets because of gas pricing, and had a bit of a competition where was the highest spread I could observe in wholesale markets, and was here in the Netherlands on the 3rd of August. When the spread was actually 516 euros per megawatt hour on electricity cost. But what I want to talk about is down here, the intraday trading. When we then go into shorter time periods in the day-ahead market, you trade electricity for a full hour, delivery of electricity over a full hour. Then if we go into intraday trading, we see 15-minute delivery windows. And the reason for that is that renewables cannot be planned. I mean, we have forecasting of renewable generation, of course, but there will always be a difference in the day-ahead forecast versus the actual day production. So there is a volatility, there's a balance that need to be, some balancing that need to be made within generation portfolios. And this is where intraday markets become relevant, where you can see that we have multiple spreads even throughout the day, especially around solar ramping, typically in the morning and the evening, where additional volatility, additional spreads exist, where energy storage can go in again and buy and sell electricity against those spreads. If we then go even a step further, we go into the continuous intraday trading, where there's a continuous trading going on for electricity to be delivered over the next 48 hours. And the interesting thing is here that you can buy and sell electricity multiple times for the same time window, depending on if you have a counterpart to trade this electricity. What that means is that for 1 hour, where you could, for example, physically deliver 5 megawatt hours of electricity, you can actually trade 30 kilowatt hours of, megawatt hours of electricity if you always find a counterpart. So then we really get into financial trading of energy, which however is only possible if you have an asset to back your financial trade up in the end. This is something that is really interesting for storage as well, because storage is this asset which can back up the trade, and it allows this continued trading. Down here, there's a graph from Inspired, which also shows the difference that can be generated with going into this intraday trading. A last notice maybe here. Also, this is a graph from Aurora, from a revenue modeling that they had done, which basically shows that for energy storage, even though frequency, like prices for frequency relation is likely to go down, and batteries will stronger participate in wholesale markets, the overall revenue levels tend to be stable. So we're not going to see what some people often say, the saturation of the market, and that the value for storage is going away. We're not seeing that because storage will migrate into different market segments, which are deeper, where it can create additional value. Just, this is actually also an interesting graph. It's a graph from the UK, how battery storage assets were traded in the UK. The UK is a bit further ahead of the German market in a sense of the kind of products and multifunctionality of products they have. And basically what you can see here, that there are certain revenues which are stable over time, and other revenues go away and are being replaced by others, but the overall revenue level is stable. Just a quick note on large-scale storage as transmission asset. Vanessa had already mentioned it, the grid booster projects in Germany, which have a different fundamental business case here. It's an asset that is owned by the transmission system operator, and it's used to reduce grid congestion cost. So it's not traded in the market, but again, a different example where energy storage being utilized, in this case as part of the transmission grid, creates great economic benefit for ratepayers, and therefore for us all as we pay our electricity rates. And just another step, so Transnet, and then there's another project for TenneT, another grid booster project to be awarded, are not singular events, but we see similar projects taking place in Spain, in the UK, in the Baltics, and outside of Europe, in Australia, in Chile, in North America. So a lot of interest in that. And a very, very quick final note, even though we see the storage market getting stronger and growing consistently, we also think that there is need for market design reform to better recognize the role of energy storage and secure investment into energy storage. We'll not talk about it in detail. We just had the European Electricity Market Design Reform consultation from the European Commission ongoing, which basically asks what should the next steps be in defining how electricity markets in Europe work. We made a proposal for volatility CFD, which is focused on securing stronger investment into energy storage as technology. So just to say, the storage market is great based on the fundamentals that I showed before. In order to bring enough storage into the markets to properly integrate the renewables that we're building in Europe, or that we're planning to build in Europe under REPowerEU, we probably need much more storage than we're currently building based on market drivers. So we believe we also need to think about market design. How can we get more investment into energy storage? Maybe somebody has a question around that later. Otherwise, thanks for your attention. And yeah, I'm looking forward to, I'll give it back to Bert and for the discussion that comes now.
Okay, thank you very much for the nice overview. For me as a not economist, always interesting. So yeah, thanks again to all the speakers. This is now the time for the people in the audience to ask questions. So you can.
So first, thank you very much for all the presenters. So I think it was an extremely interesting session. I have a question to Lars and probably Vanessa. if you want to invest in a large scale battery, let's say, with a lifetime of, let's say, 15 to 20 years, how are the possibilities to, let's say, to make an estimation on the revenues over such a long period? Because I think that you have to have a very clear vision of the future energy system in order to really quantify the possible revenues of such an installation. Will you comment on that?
Well, I can start, and then Vanessa can give us the right answer on that question.
Very good.
So it's right to the point, Andreas, and this is the question that our customers are looking at. And they're finding the right answers. The problem indeed of energy storage is that it trades in day-ahead markets where you don't know what the volatility in tomorrow's market will be. I mean, fundamentally, as we get more renewables into the grid and thermal generation goes back, we will see daily volatility. But however, how do you build your forward pricing curve based on this kind of volatility? So I think what we're seeing is that typically projects for battery scale, large scale battery projects, you would probably not plan over 20 years, but you probably look at 10 to 15 years. So there will be different kind of investors in that space. There will be the big utilities, which have a big balance sheet. Their business case is basically to put asset risk on their balance sheet. They are kind of fundamentally more fine. They might have also additional values from integrating battery storage and the energy shifting capability with their retail business. We also see other investors, which is quite interesting, which see battery storage as a de-risking of their portfolio. So if you're a renewable developer and you have 5 gigawatt of renewable assets in Germany, or you're planning to have 5 gigawatt of renewable assets in Germany, which will be exposed to price uncertainty and price volatility, potentially to price erosion. Then building 500 megawatt of battery as a de-risking of like a huge renewable portfolio is like, I mean, you're going to make revenues with your battery, but fundamentally you are de-risking your portfolio of renewable assets. And we see the same actually with people holding big storage portfolios in the UK, like Gauss Street was mentioned before. Having a battery in Germany, which fundamentally they know it will provide revenue. How much revenue will it provide? Difficult to say, but we're de-risking our existing portfolio. But nevertheless, this is one of the challenges for sure for battery storage, finding this forward curve and finding capital that is willing to invest into an asset that faces this risk of uncertain forward curves. I hope this
thank you very much.
Thank you very much. But Vanessa, maybe you have a better answer as well.
No, I think it's bringing all together, Lars, what you just said. I mean, we are here in basically kind of, it's a new venture business at some point. And so this is when you set up your business case, it's also a hypothesis based. But Lars also said it's very important that you have a de-risking strategy, even in this unknown fields of investment. And so that's important. So to which investors do you talk to, so that they get familiar with transformation and disruptive markets, and if they have the mindset to understand investing into uncertainty, and maybe also have enough capital around maybe to shape markets and so business models. So but the question, Andreas, is definitely a good one. But at the moment, to get a really proper business case, it's basically assumption based, and you need to find the right investors going along with that.
Thank you.
Okay, thank you very much. Christoph, you have a question too?
Yeah, I raised my hand because I would like to have a follow-up question to Vanessa, maybe regarding your experience with talking to investors. I would be very interested what their view on the broad technology landscape of energy storage technologies is. How is the awareness of, for example, you mentioned that thermal is the largest part of the energy demand at the end. What is their view on this? What kind of benefits are they expecting from energy storage installations?
Also a very good question. I think so. We do a lot of basic work, I would say, to that investors get familiar with energy storage systems. Because I mean, the investors I talk to, they're mostly familiar to PV, they're familiar to wind, they're familiar to grid extension, and so as energy storage systems are maybe not large-scale ones. But so they're smaller investments. They're also complex. So I mean, also following Herbert's keynote, I mean, it's not so easy just to understand it. So there's a lot of, I would say, education work and explaining how important energy storage systems are. And the more you talk to them, the more they understand it. But what I can see is it's a really a process, it's a change process also in the education of the investors so that they get familiar with that. So that's why we have those keynotes. And I think more and more conferences also from experts for investors so that they get familiar with the topic. But it's still quite what I see. It's still, so Lars, I mean, has also shown this Bloomberg graph, so where we are standing right now, and there is a huge potential. And so I think that's really important to unlock this and it's telling the story why energy storage systems are so important and understanding exactly what I tried to explain, how important it is to understand the applications and so to get the value out of this. There's still a long way to go, point.
Okay, thank you very much. So now we have in the chat some follow-up questions. Let's see about the time, but probably the first one we can do, I guess. So Vanessa, it's also for you. The question is, are you seeing much follow through with the clients signing up for decarbonization services? And if so, what were the main drivers to doing so? From Jacob Rice, the question.
Yeah, so there is definitely a more and more increasing need. So what I see on one side there, you have family offices, on the other side you have institutional investors, which are not familiar with venture and I mean venture growth cases as they are in the disruptive energy system. So there are more and more requests, and as we've seen, I mean, it's the biggest investment opportunity of our times. And so I think also maybe due to the crises we had in the recent months, the understanding is more and more there. You need decarbonization going along with security of supply and stable energy prices. And so we get a lot of requests, and so that's why we just initiated this decarbonization investment advisory services. So and understanding how important it is to have such conferences and symposia as we have it here to bring the experts and to build up the ecosystem to make proper decisions.
Okay, many thanks. I think this one is answered so far. I just see that there's one question from a Christoph, which is answered directly by Lars. So maybe I will take the chance and ask if the audience has a question directly. If not, yeah, there's one. So Harald, please.
Do you hear me?
Yeah. Yes, perfect.
Okay, perfect. First of all, I would like to thank this last speakers. It was very, very interesting to hear about the economic possibilities of electrical energy storage. I'm working now for a year about on the conversion of electricity to heat or cold by heat pumps and coolers. So for me, I automatically think of using thermal energy storage instead of electrical energy storage. So basically, if I look at the last speaker and we have 190 euros per megawatt hours and you make cold anyway of it, then you could store that in a thermal energy storage. And there is really big ones like for, what's it called, district cooling. And I wonder if anybody is thinking about this business opportunity, like the cities. If you make district cooling by electricity, you could use the storage also.
I would say yes, absolutely. I mean, I think the one big challenge that we have that, like, I mean, of course, we're looking at energy storage within the electricity sector, but like sector coupling, like making the demand more flexible, for example, through the heating sector, or in that case, cooling sector, is the key challenge that we need to understand how to translate it from a technology perspective, from an economic perspective, and probably a big piece missing is from a regulatory perspective. But I think, I mean, there are, I think, projects and companies out there who are doing these kind of things already now. But maybe somebody else.
I fully agree. I mean, as I've also shown here, this example with the heat, also with the seasonal, the Munich project. So I think so. Thanks for the contribution, because I will have this in mind as well. So, but it definitely depends then on what kind of application you have and what's the best technology then. And so it's really good to have this variety. And so yeah.
Am I still on with the
Yes.
Okay, perfect. I just want to say to Vanessa, there is a YouTube movie on an ice storage for Chicago district cooling, and this would be very interesting for you. It's the size of several buildings. I think there are 4 ice storages, and in ice storage, it's the standard to charge the ice storage when you need cold with nitride electricity. And so they are basically using this business model at the moment already. And what I think is that most of the cities which are not using something like this are not aware of it. But it's an existing technology and even an existing business model.
Yeah, great. Yeah, thank you. So I will search for that.
Yeah, it's not only in Chicago, also in Japan. In Japan, you have quite a lot of ice storage systems. So indeed, there is a market potential for it.